these lectures, the lecture, this one, this is not going to, this is not present in the NPTEL lectures, this is slightly advanced. Okay. And the problem under consideration here is the following. Suppose you assume that you have some 10 number of classes and you have observations from 10 number of classes. Then suppose, unfortunately, there are originally 11 classes, but since you don't have information on the 11th class, you only have information from the 10 classes, and somehow you have felt that there are only 10 classes. So when an observation from the 11th class comes in, you will put this observation into one of these 10 classes. So you are making a mistake. So the question is that, how do we know that when an observation comes, you should not put that into any one of the classes? Have you understood the problem? The usual pattern recognition techniques, what they do is that classification techniques. When you are given an observation, you put the observation into one of the given classes. That's what your classifier does. Now the problem is that I am looking at a problem where if I feel that it should not be put into any one of the classes, then I must be able to say that it should not be put into one of the classes. So the question is that how do we do it? Let me give you a real life example where this is needed. Okay? The example is issues regarding security. Suppose we are looking at a defense establishment in any case. Let us just say in that establishment you have 100 persons working. 100 persons. And for each person, what we have done is that you have taken the image of the person's face. Let us just say frontal view. And let us say with different expressions. Frontal view with different expressions. Say like that 10-15 photographs of one person. So you have say 100 persons. For each person you have 15 images, 15 photos. So 100 into 50, 1500 photos you have. They are there in your database. Now someone, so how it is done is that when anyone enters, there is a camera that takes the photo and then matches the photo with the given photos. That is the basic system. Now suppose I am a person who is outside the establishment. I want to enter into the establishment and do something. So I go there. Naturally my photo is not there because I am a person outside the establishment. But then what does the algorithm do? It tries to get the closest match of my photo with one of the photos. Are you understanding me? And then calls me to be that person and then allows me. Are you understanding? So the basic issue is that how does the method detect that I am an imposter? Have you understood? So here you have 100 persons means you have 100 classes. From each class you have 15 images, that is 15 training sample points. So 15 into 100, 1500, that is your total sample size, Now I am a new person. I should not be put into one of these 100 classes. The system must be able to say that I am outside. Have you understood the problem? So how does one say it? Let me tell you one another thing. I was talking about training set and test set. Shall I start from the beginning? Okay. I was talking yesterday about training set. Okay. I have some observations from class, so on and so forth. let us just say this is my whole class. Okay? That means all the observations which are here, they belong to one single class. Now I have a set of points from here. Let us just say 1, 2, 3. So these 10 points are from this class. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And suppose these 10 points are given to you as a training sample set. Are you understanding me? These 10 points are given to you as a training sample set. And now, with these 10 points, do you think you will get information on the whole space? No, you won't get it. So, if these are your 10 points, your classifier may be the best possible classifier in the world. But since your training set is not proper, you will not get good results. Are you understanding me? If your training set is not proper, your classifier can be the best possible classifier in the world. But if this is not proper, then you won't get good results. So this has to be proper. Now the question is that if these 10 points are given, to how much extent I can proceed, or I can say, how much extra I can say about the class with respect to these 10 points. Surely, one is not in a position to go to this place. Shall I start from the beginning again, or?
I think so. Some few things are also.
You can be seated here, no problem. Are expected?
Yes, sir.
Okay. Anyway, I will proceed. So if these 10 points are given, what can I say? It is true that these 10 points, you won't be able to say anything about this region. Okay. But with these 10 points, how much more we can say about the class? Okay? How much more we can say about the class? Probably, I'll just say, this is one point. Since this point is there means, probably I can say that maybe this whole region is there in the class. So this point is there means, probably this whole region is there. This point is there means probably this whole region is there. A point is there means maybe you take a disk around it, take union. So probably this whole thing will be there. The union of all these things. Now the question is, what is the size of the radius? How do you decide the size of the radius? And how do we know that what we are doing is correct? How do we know that what we are doing is correct? So, how does one look at this? Is there any name for it? How does one look at all this? So, I have mentioned to you three completely different things. One is, if the class information is not there properly, you would like to say that you want to put an observation outside the class, outside the given class. So how does one do it? That is. And secondly, when you are given a training sample set, if the training sample set unfortunately comes from one particular region, not from the entire region, then how does one say that how much extent we can go beyond this training sample point about the class? Now I will tell you the third aspect here. The third aspect is there are already some related works on this about the problem that I mentioned. That is, how does one say that this is a point doesn't belong to any one of the given classes? There are some related works in some other fields. Okay. The related works, they proceed in the following way. Say you have a system, some system, okay, and you have got an observation. You calculate the distance of this point to the given system. You calculate the distance of this point to the given system. Okay. What distance to be calculated, how to calculate it, we'll come to it later. So some distance you have. Now what the procedure does is that it puts a threshold on the distance. If the distance is less than some quantity, then you say that this point is in the system. If the distance is more than the same quantity, then you say that the point is outside the system. Have you understood it? You have a system. The example that I mentioned is that you have 100 persons in a factory or in a defense establishment. For each person you have 15 photos. Okay. So 15 into 100, 1500, that is your total system. Now a new person has come. A person's photograph you have taken, and you have somehow calculated the distance of this photograph with the 1500 photographs. Okay. Some distance. If the distance is less than a threshold value, you say that the person who is there in this new photograph is one among these 100 persons. Outside, otherwise you say that the person is an imposter. You should be put outside. So this is a basic. Now here, let me draw a diagram. The diagram is like this. On the x-axis I plot the distance. Okay. On the y-axis I plot two quantities. I am just writing them FAR, FR. I am giving you the definition. All these are available in the slides here, and a copy of the slides is already there in the organizers. Okay. FAR means false acceptance rate. FRR means false rejection rate. Let me first talk about what FRR means, false rejection rate. So you are rejecting it falsely. That is, I am a person, I am within the system. Okay. But then the rule says that since the distance of somehow my photograph with my other photographs, somehow the distance has become more than the threshold, then you say that then I am outside the system. That is false rejection. threshold on distances. So if the threshold value is very small, then what happens? You reject, your false rejection rate will be more. Let me repeat it. Say the threshold value is very, very small, then your false rejection rate will be more. When the threshold value is increasing, then your false rejection rate will decrease. Am I correct? False rejection rate, the definition is, so number of, out of the total number of observations that you have, okay, how many times you are saying that the proportion of times where a person that is within the system, you say that the person, you decide that the person is outside the system. A person who is within the system is falsely decided as a person outside the system. So false rejection. Okay? So the curve is going to be like this. Now let me talk about false acceptance. That is, this person is actually outside the system. Person is actually outside the system. Somehow you are saying that the person is within the system. Okay? Now if the threshold value is very small, a person who is outside the system, it is very difficult to put him inside the system. Right? As you increase the threshold value, your false acceptance rate will increase. So this is your FRR, this is your FAR. And this is the threshold value where those two curves meet. This is called EER. EER means equal error rate. Both the errors are equal. EER means equal error rate. Both the errors are equal. Usually, what people have done is, they have chosen this value as threshold, where both the error rates are equal. And this is what you will find actually at many places in the literature, generally outside the fractional reduction. It is called equal error rate. And there is a name for it, ROC curves. This is what people do. Now the question is, when one is doing like this, one is making an inherent assumption. The inherent assumption is that you are in a position to calculate FAR properly. You are in a position to calculate FRR properly. False rejection rate and false acceptance rate. You are in a position to calculate them properly. That is the basic assumption that you are making. One is drawing like this and choosing this one as equal error rate. Now let us just see whether that is true or not. Again, let me start with false rejection rate. A person who is in the system, you say that he is outside the system. That is false rejection rate. Since you are dealing with all these 100 employees in the organization, you can actually get good idea of FR because all these 100 employees are under you. So you can actually get good idea of FR. Now let us look at this FAR. How many persons you have outside this defense establishment? You have billions of persons. Crores and crores of people outside this establishment. Can you actually get false acceptance rate? Good idea of, good estimate of false acceptance rate? The answer is no. The answer is no. Outside this establishment you have billions. How do you take your negative sample points? and you must be able to represent the whole space. You must be able to represent the whole space. How do you get? Have you understood the problem now? So, you have a problem with this FAR, false acceptance search. So, these are 3 points that I have mentioned. Now I will go through them. Slides. So, these are the references. The main paper is Computer Vision Image Understanding. And these are the other references. Acknowledgements, actually this is a part of my students' thesis work. Face recognition. I was talking about face recognition. The users, one understands the users of face recognition. Automated reading systems are necessary, that we all know. Different systems have different scopes of or different difficulty levels. So there are many types of face recognition systems that we have. There are many tolerance levels for this recognition systems. Some systems, they can tolerate this zero effort attack. Zero effort attack means the person who is trying to break into the system, he doesn't, I should say, he does not prepare to do something extra. That means, let us just say, I have a friend in the defense establishment. I go there. I didn't know that there are so many things, so many procedures there. So I am trying to enter a system which I should not do with zero effort. Okay, my effort to enter into the system, I am not making any extra efforts to do it. And then the last one he told. Organized effort attack means I make changes in my face, probably I may put a mask, okay, I try to disguise, so that is organized effort. Now the other one, minimal effort, is in between. Now the system that I am talking about, it can only withstand this. If someone tries to do this or this, then this system that I am going to discuss is going to fail. It will not work. If someone comes out with a mask of a person, okay, who is there in the establishment, say someone is there in the defense establishment, say I put his mask on your face, then the system won't be able to say that I am an imposter. Are you understanding me? So that is organized effort attack. So in organized effort attack or even in the minimal effort attack, the system that I am going to discuss, it will fail. It will succeed only with zero effort attacks. You see, in fact, in this one there are very many other issues. Suppose I have a twin, okay, and I am working in the defense establishment. My twin brother is not working in the establishment, and suppose he comes. His face and my face are very, very close. Okay. We look very similar. Now, do you want to reject him or do you want to accept him? If you want to reject him, then you are making the threshold to be very, very small. Even, sometimes even the persons who are within the system, they may be rejected. Are you understanding what I am trying to say? And if you accept him now, he is an imposter. So you have all these things. Whenever one is devising a system, how much of where you are going to put your threshold or how much of error that you are going to incorporate, that one should do it very carefully. Okay. Assumptions. I am only taking images of faces only. Means what? Means only up to this. Suppose we have taken, all of us have taken at some point of time passport size photos, where up to this you have many times. But up to this I am not taking. I am only going to take up to this. Faces only. Okay? And I am talking about grey level images. It is true one can extend it to color images. But for the present moment I am only talking about grey level. Sizes are same. The image will have the same number of all the images that are in consideration. They have the same number of rows and the same number of columns. Okay. Illuminations are same. Suppose here it is lighted very nicely, so someone has taken my photo. And then suppose say those are all, or maybe these are all photos, and someone has taken the image of my face. And what happens is that here the illuminations are not same. Because of that, though the person is same, the gray values are going to be different. Okay? In that way, I mean, there may be a translation. One is a poorly lit image, another one is bright. Okay? So I don't have those variations here. I am assuming that illuminations are same. Are you understanding me? No background. What is the meaning of no background? If this is a background, if I stand here, to some extent the background also comes in. Right? I am assuming that the background effects are just not there. Okay. And now this one. Presence of small artifacts. What is an artifact? This is an artifact. Whether I remove this or whether I wear it, I am the same person. But then when someone takes my photograph, maybe I keep the specs. And the examples of some other artifacts: nose rings, mustache, with or without, beard. Okay, you can have earrings, and different colors of hair. Okay, different colors of hair. Today I am grey, and then maybe tomorrow I just color my hair. Okay, then it becomes black. Maybe some persons may have, I mean, in fact we see it on TV many times, different colors of hair. So, in a sense they are all artifacts. Okay. When I say presence of small artifacts, what I mean is that suppose someone is having a long beard and suppose he removes it, then the whole face it changes. So such a big change I am not allowing. I am allowing only small changes. I am not allowing big changes. Okay. In fact, we know and we can think of many examples where, I mean, some changes in the faces. We have seen many movies also. It leads to a totally different face. Okay, we have seen many movies like that. I don't need to go into all the details. I am only allowing presence of small artifacts. What I mean is that when you remove or keep those artifacts, the change in the face is very, very small. So that is the basic thing that I am doing. So these are the assumptions in the system. FAR and FR, I already mentioned it. Okay. FAR means out of all the fraud attempts, how many attempts are successful? FAR. FRR means out of all they are all clients only, they are rejected, they are classified as imposters. And then I already mentioned about this equal error rate. Okay. To obtain FRR, we need the information of faces of all or most of the circles not in the client database. Is it possible? Usual reasoning system put a point in one of the existing classes. That is one. We need a concept where data points should not be put into one of the given classes. Okay. Now I come to this. Say these points are there. Let us just say these points are there in a class. Then what can we say about that class? Okay. What I am saying is that you take a disk around it with some radius, and similarly for this point also take a disk. And take the union of all these disks. I hope you understand the meaning of the word union. Okay. Take the union of all these disks and call this set as an estimate of the class. Call this set as an estimate of the class. Okay, then when I am calling this thing as an estimate of the class, I have two questions. One is, how do I know that the estimate is good? One. Second thing is that how do I get hold of the radius? Two. Okay, one is, how do I know that the estimation procedure is good? One. The second one is, how do I get hold of the radius? Once I know the radius, and if I say that my estimation procedure is good, then I can do all these things. So first let me talk about a procedure being good. So that I do it in the following way. This definition is there in the literature. Suppose this is the set alpha. This is your original set. And suppose your estimated set is say something like this. This is your estimated set. I mean, this is what you are calling it as an estimate of this. So now, this is one set, this is another set. Take the symmetric difference. Symmetric difference means this portion, this portion, this portion, then this portion. That means all the things which is not common to both, all those areas which are not common to both. This is common to both, so the rest is this, 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 this. This is the symmetric difference. This is again a set. Then what you do is that you calculate that area, if we are talking about R2, volume, if we are talking about R3, three-dimensional space, and 4, 5, 6, 7, as many dimensions you have, the corresponding hypervolume for this symmetric difference. So in two-dimensional case, you calculate the area of this. Now as the number of observations goes to infinity, this area should go to 0. Area is going to 0 means what? Then you are getting the original shape of it. Then I call the procedure to be consistent. Then it is a true procedure. So that is the definition. Okay? X1, X2 is sequence of random vectors following some continuous distribution. Alpha is the unknown set. Alpha can be an estimated set based upon random vectors. Alpha in a set to be consistent if you take the symmetric difference, the sign delta is symmetric difference. Take the symmetric difference between alpha, the original set, and alpha n, the estimated set that you have on the basis of the n observations. Okay? And then you calculate mu. Mu is area in R2, in R3 it is volume, and there is a technical name for it. The technical name is Lebesgue machine. Since this department is, there is the mathematics is also there. I think at least some of you must be knowing what Lebesgue machine is. Okay. This is the technical name for area when you are talking about R2, volume when you are talking about R3, and R4, R5, R6, the corresponding hypervolume or whatever you call it. The technical name for it is Lebesgue machine. And E is expectation. Expectation is on an average. So that it should go to 0 and then goes to infinity. Then you call the procedure to be consistent. This is for that, the definition of whether your estimation procedure is good or not. Consistency. Now, so one has to show that the procedure is consistent. For that, there are some conditions on the value of the radius. There are some conditions on the value of the radius. Actually, these are all mathematics terms. I will not tell you the implications of these things, because then my lecture will go into a different mold altogether. So I will not tell you all these things. Basic thing that I wanted to say is that in two-dimensional case, when you take around each point xi, you take a disk of radius epsilon m. It is actually this. The distance between xi and x is less than or equal to epsilon m. You are considering all those x's. That means you are considering a disk of radius epsilon m over around xi, which is what is actually this. And then you take the union. That's what I mentioned here. Then it can be shown to be consistent estimate of alpha. If the epsilon n should go to 0 and n epsilon n square goes to infinity, and then goes to infinity. Yesterday I was talking about Kn and density estimation. There also I have two such properties. K should go to infinity, Kn by n should go to 0. And here it is something the same, similar thing. Epsilon n going to 0, n times epsilon n square goes to infinity. N times epsilon n square goes to infinity. Then one can show this thing to be consistent. Okay, this has already been done. Okay, but the problem is that how do you get hold of this epsilon? This is a similar problem that I was mentioning yesterday. How do you get hold of the value of k? Here, how do I get hold of the epsilon? Here I can do a slightly better job than what I had done for k and n. Because there are some ways in which one can get hold of this epsilon. Now let me tell you those ways. Suppose someone has taken a video camera here. He just watched me. The camera is focused on my face. Okay. Originally the expression is normal. And slowly I change it to, let us just say, angle. From normal expression to angle. So there is a video. It is taking my photo. Do you know how many photos a video takes? In just say 1 minute. How many?
11 into 16.
In 1 minute? 30. You can make it much. Hello? 1? 30. 30 frames. Right. So now I say that from normal to angle there is a path. From normal expression to angle expression there is a path. And if every point, here we are talking about video imaging, and since there is a discretization present, you have 30 photographs. Suppose the discretization is not there, that means every microsecond or so you are able to take one photograph. Then you actually think of a path between normal expression to angle. Similarly, normal to sag, you have all, if you look at all possible photographs of a person, okay, then I say that this is a connected section because there is a path between every 2 points. There is a path between every 2 points. How do I represent a photograph by a point? You can represent a photograph by a point. If you have, let us just say, 256, say it's a 256 by 256 image. You can write it in the form of a vector with 256 square, 256 into 2. You can write it as a vector of 256 square, one column vector. So this is one point. Then you have another image, that is another point. There is always a path between any 2 points. So the face class of a person is a path connected section. The face class of a person is a path connected section. Now I have 15 images of one person, which is what I started with. So 15 points in the training section. Now I have to get a connected set from there. So what is the minimal connected set that I can have from these 15 points? The minimal connected set I can have from these 15 points. See, when I put it in this way, then you have a small problem. Minimal in terms of what or etc. Okay. Then I will make it slightly better. Can you draw a minimal spanning tree of these 15 points? Yes, all of you can draw. Minimal spanning tree, you remember the definition. The sum of the edge weights is minimum. And it is also a minimal connected set. Minimal in terms of length. Am I correct? See, from mathematics I have come to computer science. Okay? From mathematics I have come to computer science. So, now one can prove some nice things regarding MST. If you have got n points, then the MST will have n-1 edges. Right? And you have n-1 edge weights. n-1 edges, that means n-1 edge weights. Now one can show that the maximal edge weight, in these n-1 edge weights, you take the maximal edge weight, where you take the edge weight as Euclidean distance between the points. Okay? And one can show that the maximal edge weight goes to 0 as n goes to infinity. The maximal edge weight goes to 0 as n goes to infinity if your set is actually it is path connected compact. Because of this compactness, some other properties they hold. One property that holds is that the maximal edge weight that goes to 0 as n goes to infinity. And the second thing is that this is your, this is me, right? If you have to make it connected, if I have to draw these discs around it, and if I have to make it connected, the union has to be connected means the radius value should be at least equal to the maximal edge weight divided by 2. Then the whole thing will be connected. The radius value should be the maximal edge weight divided by 2, then the whole thing will be connected. Okay. And the maximal edge weight satisfies, and maximal edge weight by 2 that also satisfies these conditions. So basically, this is what we are going to do. We are going to take the radius as the maximal edge weight divided by 2, and then that satisfies many properties. Okay, it satisfies those properties. I am not going into the details of those properties. Inclusion for phase class. This is what I was telling you. You can always assume the phase class to be a path connected set. A path connecting 2 points is completely contained in the set. Find the MST where the edge weight is taken as Euclidean distance. So now I will talk about M classes, M human beings, dimensionality. I will talk about PCA. I should have told about PCA in my last class yesterday. There was no time. And I have around 10-15 minutes time, so I can talk about PCA. And then I can go to this lecture. Okay? I hope many of you know what PCA is. How many of you don't know principal component analysis? Raise your hands. Okay, then let me tell you. It is like this. The basic procedure is the following. You are given, your data is in, let us just say, 100-dimensional space. Your data is in 100-dimensional space. You would like to reduce the number of dimensions. The question is, how are you going to do it? 100 is a very large number, you would like to reduce. But there is a small problem here. It is not exactly feature selection. Out of these 100 features, how do you select, say, some 10 features, 20 features? The problem is not posed in this way. Here the problem is posed in a slightly different way. You have 100 features, that is true, but you can also take linear combinations of these 100 features. So apart from these 100, you also have the linear combinations of these 100. So when you want to consider all possible linear combinations, the moment I use the word all possible, then it becomes infinite. Now how do I choose finitely many features from this infinite set? But the finite also, not 100. 100 is already given to me. It should be less than 100. How do I do it? This is the basic question. Now let us just see, when we reduce the dimension, what exactly is the thing that we want to preserve? And what is the thing that we don't mind removing? Okay. So this is the basic question that we should ask ourselves. So the one that we want to preserve, I will try to put in it. I will give an example of it. The sun rises in the east. Okay. Sun rises in the east. We all know it. We know that the sun rises in the east. So you don't go and tell your friend, hey, the sun has risen in the east today. And your friend will laugh. Right? But on the other hand, you say that today it is hot. Today it is cold. Why are we talking about hot and cold? Because it can be any one of the some combinations. There is variation. When there is variation, there is information. When there is no variation, then there is no information. The sun rises in the east, there is no information here because there is no variation. It always rises. Are you understanding me? So if the variance is more, then you have more information because you have more uncertainty. If the variance is less, you want to reduce the direction, somehow you want to keep the variance intact. When you want to reduce the dimensions, you want to keep the variance intact. Are you understanding me? So now the question is that, how do I keep the variance intact? Then what shall I do? I will do it in the following way. You have 100 dimensions, right? You have 100 dimensions. So think of 100-dimensional space. Except one dimension is 2, 3. I can think of 3, but then you should think of 100 such axes. Okay. Then you should find that direction where you have maximum variance. How do I find the direction? We will come to it later. Suppose you have found the direction where you have maximum variance. What is the meaning of maximum variance? I look at all possible directions. All possible, I mean all possible. I look at all possible directions. In each direction I calculate the variance, and then I find that direction in which you have the maximum variance. So I write down the direction. That is my first principal composition. Then what I do is that I look at all the perpendicular directions. Why perpendicular? Since my original axis is perpendicular, each one is perpendicular to the other. Am I correct? So that's why I want to get hold of new axes which are perpendicular to each other. So I have got one direction now. So I look at all the perpendicular directions. How many perpendicular directions you have? Infinite. Infinite. Among all these perpendicular directions, again I find that direction with maximal variance. That is my second principal component. Now I have two directions. Now I look at all the directions which are perpendicular to both these directions. I look at all the directions which are perpendicular to both these directions. Among them I find the one that is maximum, that has maximum variance. That is the third principal component. So I just go on and on and on doing it. So when I come to the last one means what? When I reach the 99th principal component, can I get more than 100 principal components? No. I cannot get more than 100 components. So when I reach the 99th one, when I calculate the 99th one, the 100th one is unique. There you have only one direction. That will be perpendicular to all the 99. Am I correct? Will it be only one? It will be only one. That is your x-axis, that is your y-axis, there is only one direction. Perpendicular to both. So when you have 99, when I say the direction, even this one also, I am taking it as one. So when I get hold of 99, then from 99 to 100, it's a change. So basically, when I am talking about 100-dimensional data, you can only have maximum 100 principal components. You cannot have more than 100 principal components. That is the first thing. Second one, the way I have mentioned it is, you have to find first that component, that direction. You have maximum variance among all the directions. Each time I am looking at infinitely many directions and finding that direction which has maximum variance. It's a very complicated way of doing it. Concept-wise, it is fine. But how do we actually implement it? For the purpose of implementation, what you will generally find in books is that Take the covariance matrix. This is the covariance matrix. You get its eigenvalues and eigenvectors. You have how many eigenvalues? If the it is m by m, you have m eigenvalues and you have m eigenvectors. And these eigenvalues have some nice properties. What are the nice properties? If you take any square matrix and if you calculate eigenvalue, eigenvalue can be a complex number. Right? You remember eigenvalue, characteristic roots. Eigenvalue can be a complex number. It can be a negative value also. It can be real but negative also. But when you look at covariance matrix, there are some nice properties. Covariance matrix is positive definite. Positive definite means all the eigenvalues will be positive. So you will not get complex eigenvalues. You will get real eigenvalues. Even there also you will get positive eigenvalues. You will get positive eigenvalues. And then what you do is that arrange the eigenvalues in decreasing order. Arrange the eigenvalues in decreasing order. If I call the eigenvalues as lambda 1, lambda 2, lambda m, arrange them in decreasing order. I wrote here strict inequality. I wrote here strict inequality. You may ask me a question. Is it necessarily true that they are strictly unequal? Well, most of the cases they are unequal. Sometimes you got equality. I wrote strict inequality because of some particular reason. If I want to go on telling the reasons, I won't have time. That's why it is like this. If you have strict inequality, then you can span the whole space by there is a theorem there. Okay. And anyway, in general, for our problems, the strict inequality holds. Okay. And there is another one, another nice property. I was talking about variances and preserving the variances. In the covariance matrix, where are the variances? The variances are all diagonal elements. This is the variance for the first variable. This is the variance for the second variable. This is the variance for the mth variable. And these are all off-diagonal elements. Here and here, they are off-diagonal elements. So actually, the diagonal elements are all variances. So what is the total variance? The total variance is sigma 11 plus sigma 22 plus sigma mth. This is the total variance. And one can show that the sum of the eigenvalues is same as sum of these variances. Actually, eigenvalue gives you variance. Eigenvalues, they give you the variances. Lambda 1, highest eigenvalue. This corresponds to the first eigenvector. So, the first eigenvector, the eigenvector corresponding to lambda 1, that will give you the direction. The first principal component is same as the eigenvector corresponding to the lambda 1, because lambda 1 is the highest one, and the corresponding variance value is actually lambda 1. Similarly, the second principal component is same as the eigenvalue corresponding, eigenvector corresponding to the second eigenvalue, that is the second, that is the direction, and these two directions are perpendicular. And not only that, the variance is same as lambda 2. So for these eigenvectors, the corresponding variance values are the corresponding eigenvalues. And sum of these eigenvalues is same as sum of these variances. Now someone was asking me today in the morning, how do I decide how many features, how much of dimensional reduction shall I do? Now you have to choose a quantity of your own convenience and your own satisfaction. Suppose you want to keep 95% of variances. So 5% you don't mind removing it. So then what are you going to do? You have to find a k for which lambda k plus 1 plus up to lambda m divided by, okay, sigma 1 1. This is the total variance. If I take the first k eigenvectors, first k principal components, then how much of information I am losing? This is the amount of variance that I am losing, lambda k plus 1 to lambda n. This is the total variance into 100. This will give you percentage. And this must be less than 0.5. So 5%. Choose the smallest k for which this is less than 5%. So this 5% is something that you have chosen on your own. If you feel that 5% is a large value, go to 1%. Go to 0.05. No one will stop you from doing it. Okay. Now there is another question. I am removing 5% of information. How do I know that the information that I am removing is not useful to me? That's what she was asking me. How do I know that the information that I am removing is not useful to me? My answer is that I cannot say. You are removing information corresponding to variance. The information that you have removed may be for your classification purpose or for some other purpose for which you are doing this. Maybe the most important information for that purpose, it may still lie in the place where you have removed it. Then in that case you have removed important information. Here the one that we are trying to preserve is variance. If you are happy with that, you can apply it. If you are not happy, don't apply it.
Not happy.
Then don't apply it. That's it. If you are not happy, then don't apply it. It's as simple as that. Because this is the criterion that it is using. You are not happy with this, don't apply it. Okay? Hello? No. Let me complete this. Then we'll have a tea break, then we can talk about all these things. Okay. So, here we have done the dimensionality reduction. Note that I am talking about if it is a 256 by 256 image, then the number of components will be 256 square. That is the size of the vector. That's a huge one. So I will have done dimensionality reduction and we have used PCA for it. And then afterwards we have used Euclidean distance. In fact, not only PCA, one can use many other types of dimensionality reduction. This one way is PCA, principal components. So the threshold is calculated using the minimal spanning tree and the maximal edge weight, and then we have done PCA. A new vector should not be put into the ith class if its distance with every one of the endpoints in the ith class exceeds this. Okay. This is the global threshold. Find half of its maximal edge weight. That is your threshold. So you will put a point within the system if the distance of that point to at least one of the points in the system is less than this threshold. If with every point if the distance is more than the threshold, then you will say it is outside the system. So now experiments. What are the databases that have been taken? These databases are ORL and AL. You can find them on internet, you can download them freely. AR database, we have to purchase it. Okay. Number of subjects means number of classes. In ORL you have 40 persons are there, in AL you have 50, and in AR you have 68. The number of face images per subject, 10, 11, these are the number of images in the training set per class. So out of these 10 images, 5 are taken in the training and 5 are in the test. Similarly here 5 and here 5. And then the sizes of the images, 112, here 100 by 100, 128 by 120. Now the reduced dimension. We have used several ways of doing dimensional reduction. PCA, LDA, PCA, and wavelengths. Now the number of dimensions, after the reduction, the number of, these are the dimensions, 120 dimensional space vector only we have taken. Here 39 and here 120. And then corresponding recognition rates and etc. I will not go into the details of this. Yes, in order to test our method, we had done experiments of different types. One is, we have taken the test set as coil data set. Coil data set is a collection of objects. It is just a collection of objects. Now, and we are talking about face images. So, the system should say that none of these objects should be put within this face class. It should be outside the face class. Okay, and that's what it has done. These are the 0, 0, 0s. They correspond to that. Okay. And then for training we have taken A, test you have ORL data. Then also here you have 0. That means none of the points in the ORL, these persons are naturally different from these persons. Okay. So these are all imposters. So that's what is given here.
Sir, using assumption you prove the size will be same, but ORL and A database do not have the same size of the images.
But we are reducing the dimension. That we can take our own sizes. Okay. That we can take our own sizes. We are reducing the dimension. See, once you do the dimensional reduction, then you can keep so many things together. Now, this is the main thing. Compare them with ROC, curve-based threshold correction. So, if I want to do the comparison with this method, what I need to do is that I must be in a position to calculate FAR and FRR. And in order to calculate false acceptance rate, I need to have negative samples. So basically, what is happening? I have a training set, 40 images, 5%. Then I have this many imposters to get the value of FAR, false acceptance rate. I have this many clients to get a value of FRR, false rejection rate. To get false rejection rate and false acceptance rate, I am using this. Then this is the test set. Test set, these many imposters are there and these many correct clients are there. So I have to make different such combinations to test whether the proposed method works better than the existing method. And those many 10 such different combinations are taken. And then the corresponding recognition rate. If the imposter is classified as imposter and client is classified as client, that's fine. If a client is classified as imposter or imposter is classified as client, then that is misclassification. So recognition rate, this is correct recognition rate is M1 out of M clients are classified correctly, N1 out of N imposters are classified as clients. That is, N minus N1, you have these many imposters, here you have N number of imposters. So these are all correct classification. Now this is the comparison. Now the proposed method. He is giving 97.25 here, he is 95, 98, 94, 96, 95. Consistently, these figures are less than this. Consistent. And extension to kernel, you see. Your questions.